Hello everyone, I'm Seung-Jun Kim, Associate Professor at Korea University. Today, I'd like to share our latest study result about the transmission tower. So, the title of my presentation today is Study on Failure Mode and Load Carrying Capacity of a Transmission Tower. This is content of my presentation today. Firstly, I will briefly introduce the transmission tower. After that, I will show you the general information of structural design specification. And then I will introduce the ultimate behavioral characteristic of transmission towers investigated by finite element method. And then I will introduce our full-scale experiment details. And then I will make the conclusion. Let's see the general definition of the transmission tower. As you can see in this simple figure, the transmission tower is nothing but the structure for supporting the overhead transmission lines shown in the figures. So obviously the transmission tower is one of the lattice structure. Therefore, this structure consists of the actual members like main post, horizontal member, and bracing. The horizontal member and bracing are designed in order to enhance the buckling strength of the main post. Although the main object of the structure is to support the overhead transmission lines, obviously the wind load govern the structural design. Therefore, we should carefully deal with the wind load effect when we design the structure. Recently, some alternative type have been developed for the transmission towers for the high voltage transmission line, especially. But still, this transmission tower, the lattice type tower, has been mainly designed and constructed. As you can see in this figure, we should consider the sufficient clearance between the ground and lowest conductor for the safety issue. Therefore, if the voltage of the system is increased further, the tall tower is required. For example, in Korea, 345 kilovolt class is mainly constructed for transmission line. In that case, the height of the tower would be 70 meters around. And then for the higher voltage systems, like the 765 class, then 150 volt towers are constructed. Recently, Korea Electric Power Company, KEPCO, announced they will construct the new transmission lines at the east coast of the Korea. In that case, the class would be 500 kilovolt. So the tower's height would be 100 meters around. These are the design specification of transmission towers. The first one is a design code in Korea, published by KEPCO. And the others are the international code. As you can see in this table, except this one, the compared design specification has been established based on LRFD method, but DS1111 Korean specification is still based on ASD, a lower stress design method. Obviously, this document is firstly established in 1980, no, 1970. Although this document has been updated several times, but still this one is based on ASD. But as you know, if we consider LRT method concept, then we can apply the rational load and resistance factors to consider the uncertainty of the load and resistance of the members. Therefore, many of documents for the various infrastructures have been developed based on LRFD method. So nowadays, KEPCO recognized about this limitation and this issue. So they decided to update the document from the ASD to LRFD concept document and specification. So our group has been involved about this project. So we are taking the task about the suggestion of the new LRFD concept document. And in order to back up the new design criteria and design specification, we have conducted the various simulation and experimental researches. In order to define the limit state of the structure rationally, we studied about the collapse examples like that. So as you can see, in many cases, the excessive wind load has induced the collapse of the transmission tower in operation. But some accident has occurred in construction and even maintenance stage. So we tried to make the new design specification involving the rational criteria for checking the structural safety at the construction and maintenance stage, as well as the operating condition. And then we have carefully reviewed whether the design wind velocity should be updated or not, considering the climate crisis. And due to the time limit, I cannot show you some issues of the current design specification in detail, but as I mentioned before, basically these criteria were summarized based on the ASD method. So firstly, we should adapt the new concept, like the LRFD concept. And as you can see here, I'm sorry about so many Korean words. Because this document were summarized based on ASD, we can see the definition of the factor of safety. But as you can see here, every members will be designed with the constant safety factor of safety. That was 1.5. And then for the buckling strength calculation, we can see the two distinguished equations. There are some parameters which will be included in the equations. According to the equations, we can expect the equations can be classified for elastic buckling and inelastic buckling, but we cannot clearly see the reference about the equations. And the transmission tower will be fabricated by using the angle tie members and even some hollow section steel pipes. And there are so many details about the connection between the members. For example, the connections between the main post, between the main post and the horizontal members, main post and the bracings, all the connections are different. So we should carefully check the impact of the different connection types on the buckling resistance of the members. Also, we should clearly reflect the impact of the residual stress. So during the revision, we reviewed so many equations about the buckling load calculation, especially for the angle tie members and hollow section members. So we are summarizing the rational equations about the calculation of the nominal buckling strength of the members. That is the first issue. Also, there is some useful table. That is the table of the equivalent wind pressure. By the way, in the previous version, the equivalent wind pressure, the single pressure will be applied to every member of the single towers. That is a nonsense because every point, the wind velocity will be varied. So we checked whether this table is rational or not. Also, there is another table. This table is the stress combination for evaluating the maximum stress of each members. Because we can use a three-dimensional FE model when we design the structure. And if we clearly define the load combinations, then I think those kind of combination table is not necessary. So we also check whether this table is rational or not, and effectiveness of this table for simple design of the structure. So we will decide whether the tables will be erased or not. Now we go to the main topic about this presentation. So I will show you the ultimate behavioral characteristic of the transmission towers investigated by the nonlinear analysis. Mainly, I will show you the analysis result by using three-dimensional structure like that. So as you can see here, the structural model were prepared by using line members. By the way, we used the beam element for the main post and horizontal members because we considered the details of the connection between the main posts and the horizontal members. And then the bracings were modeled by the truss members. Obviously, as well as the entire model, we also conducted the extensive parametric analysis study about the part or even some members. But due to the time limit, I will show you the result about this entire model. And then, as you can see here, mainly we conducted the nonlinear analysis in order to consider geometric and material nonlinearity. By the way, when we conduct the nonlinear analysis, we should consider the imperfection of the members. So in order to extract the rational imperfection module shapes, we will take the eigenvalue analysis before the nonlinear analysis. By the way, because the structure have so many line members, we decided to consider the irregularity of the imperfection of every members. Therefore, report to the previous papers published in engineering structures, we take those kind of multi-imperfection shapes. And then by using the superposition rule, we made some irregular imperfection shapes by using the multiple module shapes of the eigenvalue analysis. And then we applied this imperfection. Then we take the nonlinear analysis. After nonlinear analysis for the various load cases, then we take the load displacement curve like that at every point. And then we check one member will be firstly collapsed or failed, and what types failed mode is observed. Then we may check the first yield point, and then we will check the sequential failure of the members. Then we may check the ultimate stages characteristic of the structure. As you can see in this slide, we examined the various types of the transmission towers, taking the various voltages level and some suspension types like that. For example, the 154 kilovolt class towers has the height of 45 meters, but for high voltage class, then the height of the tower is increases further. For the 345 kilovolt class, then height of the tower would be 70 meters. But for this one, the height reached to 120 meters. And for the 4 towers, the main posts were designed by the anchor member. But for those kind of high-rise tower, the main posts will be fabricated by those hollow section steel pipe members. So although the height of the structure is very long, very high, the structural stiffness of the entire structure will be larger than the previous models because the hollow section pipe is applied to the structures. This is an analysis flow for our simulation study. Firstly, we will take the eigenvalue analysis in order to investigate the elastic buckling behavior of the structures. Obviously, the eigenvalue analysis does not include the nonlinear effect. So there would be the difference between the maximum load factor or eigenvalue and the maximum load factor obtained by the nonlinear analysis, because when we take the nonlinear analysis, we can reflect the nonlinearity of the materials. Then we may check whether the material nonlinearity is significant or not. These are the loadings. So as you can see here, we examined the totally 22 load cases, design load cases from our LRFD concept specification. First, the case one is about the intact condition. So I mean, all wires are connected. But as well as the intact conditions, we also examined some damaged conditions. So I mean, the case two includes the load induced by some wire broken. So GW means a ground wire, which is attached to the top of the towers. So one of the line will be broken for the case two. Case 3, 4, and 5 are another damaged conditions. So for example, the case 3 includes the load induced by the first conductor here is broken. And this is another intact condition. By the way, this is for the low temperature condition. Because if we consider the low temperature condition, the design wind velocity will be reduced compared to the case one, but we will include the snow load effect. Therefore, we may check what load cases are more governed about the ultimate stage of the structure. This is a boundary condition. Boundary condition is very simple. So as you can see here, the bottom point of every leg will be fixed. This is a material property. Because we use a simple structural steel, we simply use elastic and compact plastic model like that. And yield strength of the material was 400 megapascal. These are the result of the eigenvalue analysis. So by using the eigenvalue analysis, we may track the elastic buckling strengths and the corresponding buckling mode shapes. So for example, the 154 kilovolt class tower has eigenvalue of 2.03 about some critical load case. So it means that will have the 100% margin about the elastic buckling, perhaps. But as you can see, because we use a very large diameter hollow pipe for the 764 kilovolt tower, the eigenvalue is very large compared to the previous small towers. Right? So please remember this number, 6.68. And we also does not include any nonlinear impact. Now, this is one of the nonlinear analysis result. This is about these 764 kilovolt class towers. Although the eigenvalue about this one was 6.68, the nonlinear analysis result indicate very small maximal load factors about the same load cases. So when the load factor reached to 2.849, then this member is firstly buckled. And we checked this one showed the inelastic buckling, not elastic buckling. After that, as the load increases further, the additional members are buckled. And the final stage, the members at the compression zone are buckled, and all the members showed the inelastic buckling, not elastic buckling. So according to this result, this tower has a 200% margin about the ultimate staging. And we also we are investigating the result of the simulations. Because we have so many data, we should spend so many times. This is one of the comparative result. So although we apply the different imperfection level, the imperfection does not significantly affect to the result of the simulations. In general, the imperfection is one of very influential factor about the load carrying capacity of those kind of cylinder structures. So we are taking some investigation about this one. Now I will show you the full-scale experiment. The object of this full-scale experiment are here. First, through this experiment, we will investigate the governing design load case of the ultimate behavior of the towers. And then we will see the weak part of the structure. And then based on the experimental result, we will validate the summarized design code as well as our analysis method. For this task, we designed 4 different transmission towers. Obviously, the 2 models were already examined the last month, and the next month we will take the experiment for the remaining 2 models. And 2 models are designed for 354 kilovolt class towers, and another 2 towers have the hollow section main post. And as you can see here, for each model, we will apply 8 load cases. And 7 load cases were revised as a subload level in order to check the structural integrity under the subload level. And then the last one case will be examined until the structure is collapsed. So this is a load sequence follow the procedure of IEC 60826 code. That the name of this code is a design criteria of overhead transmission line. And this code specifies the loading sequence about this load test. In Korea, the new designed transmission tower should pass those kind of load tests for the selected load cases. By the way, please remind that every existing towers designed based on the ASD code. It means that all the design load are the subs load levels. It means that we can simply apply the 100% of the all the design load cases. By the way, our models are designed based on the LRFD concept. And as you know, all the design load cases of the LRFD code have the load factor exceed 1.0. It means that we should revise the quantity of the design load from the load case 1 to 7 in order to check the integrity in subload level. But at the beginning, we missed it. And after that, the last load case will be applied in order to check the ultimate behavior of the towers. This is a figure of the model. So as you can see here, the height of the tower was 70 meters. And these are the loading points. As you can see in this picture, we used the wire and winch in order to apply the designed load at the selected point. And then we attached some mark in order to measure the displacement by using drone. And we also attached the strain gauges to selected members. By the way, we believe the bending moment will make the significant stress at the members. Therefore, in order to validate the contribution of the bending moment on the normal stress at the sections, we attach the multiple strain gauges to the same sections like that. As you can see here, during the operation of the experiment, we obtained the data at every point about the strains. Then we can investigate the level of the stress during the load test. And then Professor Young-Gyu Chu, the director of Building Forensic Engineering Laboratory at Korea University, used the drone in order to have some videos. So the video will be used for post-process in order to extract the displacement during the test at the selected points, as well as the displacement. And he can extract the natural frequencies and corresponding pre-vibration mode shape of the towers. So this method will be, this task will be used to validate their forensic engineering techniques. Because of the time limit, I cannot show you the details about this one. As I mentioned before, at the beginning, we had some mistake. The towers were designed based on the LRFD concept design. It means that all the selected load cases include the load factors. So in order to check the structural integrity in surface load level, we should erase the effect of the load factors, but we could not this task before the first experiment. Therefore, unfortunately, the model were failed during the 5th load case test. This video shows the deformed shape due to unexpected collapse. Here. The 5th load case includes the load effect due to this conductor failure, broken. So due to the excessive torsion as well as the compression, this member between this arm and this arm were buckled. So we tried to erase all the members above these failed members, and we reconstruct the tower model. Also, as well as the tower, we also revised the load cases for the test from the case 1 to case 7. Then we revised and we prepared the service load level load cases again. Then we take the the experiment. Then from the first load case to 7th load case, we check the structural integrity in the service load level. And then we compound the maximum stress level does not reach to the yield stress. Even, obviously, the maximum stress were less than 200 megapascal, which is half of the yield stress of the members. And then we finally apply the last load case until the structure is fully failed. So this one is a failed mode shape. The same part showed the same buckling. So we can compound this one is one of the weak part of the towers. So again, this is a brief summary. For all the service load level cases, the maximum stress were under the 200 megapascal. That was a half of yield strength. Also, the load factor, maximum load factor obtained by the experiment were 1.1. It means that this structure has the 10% margin about the failure. Especially the resistance factor about the buckling of the main post were 0.9. Therefore, this 10% margin is very reasonable. And then this is the second model about this experiment. Obviously, KEPCO presented their designed model, and the model was designed by the AES-based code. So from the model, the reference model, we updated the design considering our LRFT-based code. So we confirmed that the main post section could be reduced like that. By the way, in order to enhance the buckling strength and buckling resistance about the weak parts, we tried to increase the section of the bracings. And then we also attached the strain gauges to the target points. Then we also take the simulation for experimental models by the eigenvalue analysis and nonlinear analysis. So by taking the by taking eigenvalue analysis, we obtained the minimum eigenvalue that was 2.22. By the way, if we take the nonlinear analysis, the maximum load factor was 1.25 for the last load case. And then from nonlinear analysis, we checked the one members would be buckled during the test. This is the experiment of the second model. So when we apply the last load case, the members between the arms are not buckled. As you can see here, the member near the body were buckled. And the same point indicate the same members, buckled members from the experiment and the simulation. And final load factor or maximum load factor of the experiment were 1.3. But as I mentioned before, the maximum load factor obtained by the simulation was 1.25. So we can confirm our analysis method can be reasonable, is reasonable, and we can confirm our design code are very reasonable. Okay, due to the time limit, I cannot show you the details about the conclusion. Anyway, we have studied about the ultimate behavioral characteristic of the transmission towers by the simulation and the experiment. And those kind of result will be the evidence of the newly summarized LRFT-based design code for the transmission towers. And as I mentioned before, we will take the additional experiment the next month. After finishing all the planned experiment, we will spend so many times to handle the details data from the experiment as well as the simulation. And then we will summarize and confirm the LRFT-based design specification for the transmission tower in Korea. Okay, if you have any questions or if you want to have some additional information about our simulation or even experiment, then you can really contact me at here. Okay, thank you for your listening about our presentation.